In The Legend of Zelda Majora's Mask, the titular Majora's Mask is causing the moon to fall onto the land of Termina. Link only has 3 days to stop the moon from falling. But have you ever wondered how destructive the moon would be? Well, let's find out. To find how destructive the moon would be, you would need to find out how much energy is caused by the impact. To find the impact energy, you need to find the moon's kinetic energy while it's falling, which you can use the equation kinetic energy equals 1/2 mass times velocity squared. Let's figure out velocity. In the real world, you would use gravity to figure out velocity, but since this is a fictional world with fictional gravity, we don't know how strong it would be. So let's find out the velocity the hard way. First, we need to find out how high up the moon is. And to do that, we need to find out how big Link's feet is. To find that out, you just compare the height of Link, 3'10", and Link's feet. Using a ruler, I was able to determine that Link's feet are 6.5 inches long. Now that we know the size of Link's feet, we can use his footsteps to count the distance between right under the moon and this tree stump. Link took about 220 steps in total, which converts into 1,400 inches. Since Link's steps aren't the most accurate way to measure distance, I'm going to be using significant figures throughout this. Significant figures are just is just a way of rounding when doing scientific problems. Now let's zoom out from this stump and create a triangle with the points between the stump, right under the moon, and the moon. Now we know the points between the stump and right under the moon is 1,400 inches, and this is a 90-degree triangle. So we can use a tangent function to figure out how high up the moon is. If I use my protractor to find this angle, a tangent function is set up like this. Tangent of 62 degrees equals opposite over adjacent. Now we can plug in the points between under the moon and the stump right here. And if we use some algebra, we can figure out that the moon is 2,600 inches in the sky. If you remember, it takes 3 days for the moon to crash into Termina. So we can use that to find our velocity, which comes out to 36 inches an hour, or 0.3 times 10 to the -4th meters per second. That's slow. Like, really slow. Now, to find the mass of the moon. To find the mass of the moon, we need to find how tall the moon is. I can't really figure out how tall the moon was by myself, so I googled it. And found this image by Says How Mall, explaining how tall the moon is. They used pixel counting, which is a similar but more accurate method to what I did to find the size of Link's feet. It's where you count the individual pixels on your screen and use that to compare an object which height you already know and another object. They used it to compare Link's height to the head of a giant. And then they used the giant's head to find the height of the moon. Now that we know how tall the moon is, we need to find its volume. To find its volume, we take the equation volume equals 3/4 times pi times radius cubed, and plug in the radius of the moon, which is half the length of the moon, which comes out to be 270,000 meters cubed. Now we take the volume and multiply the density of the moon to get mass. The average density of a moon rock is 3.3 grams per meters cubed, which when you multiply by 270,000 meters cubed, it comes out to 901,000 grams, or 901 kilograms. Now that we have both the velocity and mass of the moon, we can go back to the kinetic energy equation and plug in mass and velocity, which comes out to 0.4 times 10 to the negative 7th joules. That is very weak. A stick of dynamite is more powerful than that. This means that it crashing into Termina would be less of crashing and more of just bumping into it, causing no destruction, which is pretty disappointing. I was hoping for it to be as powerful as a nuke or something like that. But nope, it's weaker than a slap. Well, anyways, thanks for watching.